Imagine this. You're staring up at the night sky, those twinkling stars scattered like diamonds on black velvet. And you wonder, what's the ultimate fate of all this? Will the universe just keep expanding forever, getting colder and lonelier until everything fades into nothingness? Or could it all come crashing back in on itself like a cosmic boomerang? Well, buckle up, because recent data from astronomers is flipping the script on everything we thought we knew about dark energy, the invisible force that's been pushing the universe apart. In this video, we're exploring how dark energy might be losing its grip and what that means for the end of everything. If you're as obsessed with space as I am, hit that like button and subscribe so you don't miss out on more universe-shaking updates. Let's jump in. First off, let's rewind to the beginning, because to understand where we're headed, we gotta know where we came from. About 13.8 billion years ago, the Big Bang kicked off the universe in a massive explosion of energy and matter. Everything started expanding outward, like a balloon inflating at insane speeds. For decades, scientists figured gravity, from all the stars, planets, and galaxies, would eventually slow that expansion down, maybe even reverse it, leading to a big crunch, where everything collapses back into a single point. Or, if there wasn't enough gravity, it'd just keep going forever, ending in a big freeze, a cold, dark void where even atoms drift apart. But in 1998, two teams of astronomers dropped a bombshell. They were studying distant supernovae, exploding stars that act like cosmic yardsticks because they always shine with the same brightness. By measuring how dim these explosions looked from Earth, they could figure out how far away they were and how fast the universe was expanding. What they found? Not only was the expansion not slowing down, it was speeding up. Like the universe is accelerating away from itself. This discovery earned them the Nobel Prize in 2011, and it introduced us dark energy. So, what the heck is dark energy? Picture it as this mysterious, repulsive force woven into the fabric of space itself. It's not like regular energy or matter. It doesn't clump together or interact with light, which is why we call it dark. We can't see it directly. In our best model of the universe, called lambda CDM, that's lambda for the cosmological constant, CDM for cold, dark matter, dark energy makes up about 68% of everything. Dark matter is another 27%, holding galaxies together with its invisible gravity. And the stuff we know, like stars, planets, and you and me, is just a measly 5%. Dark energy is what keeps the pedal to the metal on cosmic expansion, counteracting gravity's pull. Think of it like this. Imagine you're on a skateboard, and gravity is like a hill trying to pull you back down. But dark energy is an unseen wind at your back, pushing you faster and faster uphill. In the standard model, this force is constant, like Einstein's cosmological constant, a fixed property of empty space. But other ideas float around, like quintessence, where dark energy is a dynamic field that could change over time. For years, we've assumed it's steady, leading us to predict a big freeze. Galaxies race away from each other, stars burn out, black holes evaporate over trillions of years, and the universe ends not with a bang, but a whimper, cold, dilute, and eternal. But here's where things get exciting and a little scary. Fast forward to 2024 and 2025, and data from the Dark Energy Spectroscopic Instrument, or DESI, is shaking things up. DESI is this powerhouse project based at the Kitt Peak National Observatory in Arizona. It uses a massive telescope with 5,000 robotic fiber optic eyes to map the light from millions of galaxies. By analyzing their spectra, the rainbow of colors that tells us how fast they're moving away, thanks to redshift, DESI creates a three-dimensional map of the universe spanning 11 billion years of history. What did they find? Evidence that dark energy isn't constant after all. It seems to be weakening by about 10% over the last 4.5 billion years. They measured this using baryon acoustic oscillations, or BAOs. These are like giant ripples frozen into the universe from its infancy, when sound waves sloshed through the hot plasma right after the Big Bang. BAOs act as a standard ruler for cosmic distances. By comparing how these ripples look in nearby galaxies versus distant ones, DES spotted a mismatch. The expansion rate isn't holding steady. If dark energy is fading, the universe's acceleration could slow down. Now, let's unpack what this means. If dark energy keeps losing power, gravity might win the tug of war. Expansion slows, stops, and then, bam, reverses into contraction. Hello, Big Crunch. Everything hurtles back toward a singularity, heating up to insane temperatures, potentially resetting the cosmos in a new Big Bang. Some theorists love this idea of a cyclic universe, where bang follows crunch in an eternal loop. It's poetic, right? No endless void, just rebirth after rebirth. But hold on, don't cancel your plans for the heat death just yet. This isn't set in stone. The DESI results are intriguing, but they're only at 2 to 4.2 sigma confidence. Statistically speaking, that's like a maybe rather than a definitely. In science, we need 5 sigma for a true discovery, like the Higgs boson. There could be other explanations. Maybe our measurements have systematic errors, like how dust or evolving supernovae brightness throws off data. Or perhaps dark energy isn't weakening. Instead, we're in a giant cosmic void where local expansion looks different. This ties into bigger debates in cosmology. Remember the Hubble tension? Different methods measure the universe's expansion rate, the Hubble constant, and get conflicting numbers. Around 67 kilometers per second per megaparsec from cosmic microwave background data versus 73 from supernovae. DESI's findings lean toward the lower number, but if dark energy is evolving, it could resolve that puzzle. Alternatives to lambda CDM are popping up too, like modified gravity theories. These tweak Einstein's general relativity, so we don't need dark energy at all. Maybe gravity behaves differently on cosmic scales. I mean, this isn't the first crisis in cosmology. Back in 2011, there was hype about neutrinos traveling faster than light, which would have upended physics. Turns out, it was a faulty cable. Science is all about testing, refining, and sometimes scrapping ideas. That's what makes it thrilling. We're piecing together the universe's story with new tools every day. So, what's next? DESI isn't done. It's got years of data collection ahead, aiming for 40 million galaxies mapped. Other missions are joining the hunt. The European Space Agency's Euclid satellite, launched in 2023, is scanning the sky for dark energy clues with its wide-field imager. Then there's the Vera C. Rubin Observatory in Chile, set to start its legacy survey of space and time soon, photographing the entire southern sky every few nights. These could confirm if dark energy is indeed fizzling out, or if we're barking up the wrong tree. Wrapping this up, the idea that dark energy might be running out of steam is a game-changer. It challenges our cozy model of an eternally expanding universe and opens doors to wild possibilities like cycles of creation and destruction. Whether we end in a freeze, crunch, or something else entirely, one thing's clear: the cosmos is full of surprises, and we're just scratching the surface. What do you think? Big freeze or big crunch? Drop your thoughts in the comments below and let's discuss. If you enjoyed this, smash that thumbs up, subscribe for more space adventures, and turn on notifications. Thanks for watching. See you in the next one.